evening, everybody. It's great to see you all on this Friday night. We're looking forward to having a talk by Dr. Dan Fabrici, who's a professor at the University of Chicago, although right now, and he may share this, he's working for the National Science Foundation as a grant reviewer, is that right? And living in Northern Virginia. But he's a tenured professor at University of Chicago. We've had some interactions, and he visited the Bradley Study Center a couple of years ago, and we invited him back. So we had this afternoon and tomorrow morning a seminar for students, undergraduate and graduate students, in the study center where we're delving more deeply into astrophysics and questions of meaning and purpose and the Christian faith and the relationship between science and religion. And I was really excited. We had 10 students, and they were all really engaged, and we're looking forward to seeing them again tomorrow. So we're getting really kind of six or 7 hours of contact hours with Dr. Fabrici while he's here in town, and having some really good discussions at the tables this afternoon, and we're looking forward to that as well tomorrow. And so we figured that while we're bringing him in town for that seminar, that we would also offer a public lecture. And so that's what we're doing tonight. This is the first time the Bradley Study Center has offered a lecture in the church and not on campus. And the main reason is because the campus now charges for parking after 5 p.m. And I actually met with the director of parking to see if there's anything we could do about it, and there isn't, because we're just like any other group. And so once in a while, we want to offer things to the community for people that would find getting on campus to be inaccessible. So we're looking at having them probably in local churches. So this is the first time we're doing that. This is also the first time we're doing an event on a Friday night, and we'll see how well that goes. But we're really excited about what Dr. Fabrici has to say tonight. And so I've already said he is a professor at University of Chicago. His expertise is exoplanets. I'll let him explain what an exoplanet is, because I'm sure I'll get it wrong. So in case you aren't aware of the Bradley Study Center, we're a Christian study center at Virginia Tech, and our mission is to help students and faculty connect their faith with the work that they're doing in the life of the university, and to provide a thoughtful Christian presence to the university, which I think is desperately needed in the university today. And so those are the two things that we do. We work with campus ministries to do events, and we also work with the university on occasion to do events. And then we host events like we're doing right now with students, formative events that give them an opportunity to really dig deep on questions that are important in our society today and the interface between science and religion. So anyway, we're really glad to have you here tonight, and we're really pleased to have Dr. Fabrici. And so I will turn the floor over to him. Thank you.
All right, welcome, everyone. It's great to be here. Hi, Shane. It's a pleasure to be here in Blacksburg, and I am at the NSF at the moment. I'll show a picture from a colleague of mine coming up, and I'll just start off with exoplanets. What is that? They are planets that are orbiting around other stars besides the sun, and we've known them since about 1995. They've won a Nobel Prize recently for that first discovery, I'll just briefly talk about them a little bit. So this picture at the beginning here, that's me down at the bottom showing off the universe, so a little astrophotography selfie. And this was taken a few months ago in Iowa. And if you really know your sky, you might be able to tell some things in here. But I'll show you what they are. This is right before astronomical twilight, so it's early in the morning. Could you go to the next one, Matt? Okay, here's the hint. It was spoken about maybe 4,000 years ago, whenever Job was written, one of the first books of the Bible to be written. Can you bind the chains of the Pleiades or loose the cords of Orion? That's speaking to man, are you as powerful as God? And at the very tippy top of that image, you can see a little group of stars. If you go to the next one, it blows it up here. These are the Seven Sisters, or Pleiades, or Subaru, a little cluster of rather young stars that have recently formed and are still orbiting around in their orbits about each other. And then right above my hand, if you go to the next one, and I flip it vertical, you might recognize this as Orion. So I'm gesturing right there at Orion's belt, and that's those 3 stars. When you flip it up like that, that's horizontal. So, and the other really famous one in that constellation is Betelgeuse at the very top of this image. So that this is just a regular DSLR camera with a long exposure, and I don't recall what it only goes up to 30 seconds on my camera, and the stars would start to trail if I went more than a few seconds. So I think this is just a few second exposure. But when you look at it just by eye, you can tell it's pretty red. That's what Betelgeuse is famous for. And then the other part of this constellation that I'm going to get into later is the next box, which is the Sword of Orion. And in there's a cluster that is still in the midst of forming. It's called there's the trapezium, which is 3 bright stars, and then a bunch of gas and dust around it. All right. What else do I want to say about this? Well, the next figure shows a zoom in, and this is the existential question. So zoom in on the person. When I look at your heavens, the work of your fingers, the moon and the stars, which you have set in place, what is man that you are mindful of him, and the Son of Man that you should care for him? And it goes on to say that man's place in the cosmos is a little lower than the angels, but is crowned with glory and honor. Now, that's just a guy out in the field. But what is the connection between the grandeur of a peaceful night and the existential questions of where we came from? Let's go on to the next one. That was just zoomed out, wide field view of the cosmos with a regular old camera, taking a few second exposure. And you saw some streaks in there too. Those were planes going by in the early morning, and there was even a contrail in there. So that's kind of a cruddy image, right? But this is one of the humanity's first real hard tries at a beautiful, beautiful deep image. This is the Hubble Ultra Deep Field after our space telescope went up, and it's a 4,000 by 4,000 pixels, so a 16 megapixel camera. So that could fit in your phone nowadays, but back then, plus a few years for radiation hardening before it was sent out into space, this was really top of the line, advanced camera for surveys. And they found a spot on the sky that didn't have any contrails, that didn't have any foreground stars, and just sat on it and said, okay, universe, what do you have to offer? If we take this thing if we take a 2-week exposure, what's going to crop up in the universe? And the answer is a lot of really, really distant galaxies. So just about everything in that image there is not an individual star in our galaxy, but it's another whole galaxy off in the universe. So if you click the next one, you can see these images come served up to you from the US government because they are taxpayer funded. And so you can download your 110 megabyte image of the Hubble Ultra Deep Field. And then if you go on to the next one, we see the new kid on the block. This is the James Webb Space Telescope, launched at the end of 2021. And its first light images were in July after ridiculous and ridiculously scary unfolding of this telescope, because it's a 6.5 meter telescope, and that had to fold up into a rocket. So it had a lot of moving parts, which is not really what you want from an engineering perspective. But it unfolded, and it has a golden coated mirror because it's not intending to take a lot of visible light, but rather infrared light. So that is better for these high redshift galaxies, which it can see. This particular image is the first glamour shot of the high redshift universe from James Webb. It wasn't nearly as long in exposure. You can see a spider, like a star with lots of flares in the middle there. So there is one nearby star that's in there. I think about, okay, and then in the bottom right, there's another one. Almost everything else is a galaxy. And you can see some kind of swirling motion to this thing. It's not just a random spot on the sky, it's a cluster of galaxies. And this cluster of galaxies has more galaxies in the distance beyond it. And when their light passes the cluster in the foreground, it gets bent around. So you're seeing distorted images of those background galaxies. And so the universe, with all its mass, can deflect the light from background galaxies. So I think what you're getting the picture of, which is how we think of it nowadays, is how chock full the universe is of galaxies. And nevertheless, there is a paradox, which is, since as you go further and further away from us, there's more and more room out there for stars and galaxies. You'd think that however far you go, you'd eventually hit one star. So the resolution, that's the Olbers paradox, and its resolution is twofold. One, there's dust in the way sometimes, and that shifts the light from the visible spectrum to infrared, and so our eyes won't pick up. But more important is that the universe is a finite age, so the light can only come from a certain distance. And beyond this distance, where some of these redder galaxies are, the galaxies simply haven't formed yet. So this is something new that we're learning, like the edge of the distribution of galaxies. There have been lots of reports out there about James Webb precipitating a crisis in cosmology. It's not really as bad as perhaps it seems. The Big Bang is still strong and kicking in astronomy circles. It's just that we have to modify our ideas of how efficient stars are at forming, and in what kind of clustered situations they can form, and the mass distribution at which they form. So I'm just planting flags like that in the ground so that you'll start thinking of questions for the Q&A. Let's go on to the next one. Here's another glamour shot from that first 2022 set of images. This is the Carina Nebula, and it just looks really cool. It looks like a mountain range of gas and dust, with stars being formed in the gas and dust, but also stars raining down their photons on the front, on the edge there. All right, go to the next one. In the promotional materials for this talk, you probably saw the pillars of creation, which is on the left, and I just learned that this was a phrase that came from a preaching by Charles Spurgeon, so one of our greats. And the idea that creation itself is held up on pillars, and God is active in the world, even through those things that are being made, because we know from Colossians that there's nothing made that Christ didn't make. So in this cluster here, or in this set of dusty pillars, they become pillars just kind of like comets do. They're getting radiation from off to the top right. Hot stars are shining on it, and then that etches them away into a tail. And so this is how those things are formed. But deep inside of those dusty pockets, stars are forming. And so star formation takes a million or 2 years, typically, from the beginning to crunching down and blowing away in the envelope. During that time, we can sometimes see planets forming around those stars. And here's our most familiar planet that we see out there in the night sky, Jupiter. And in fact, if you know your constellations extremely well, in that opening plot, you'll have noticed a pretty bright star between Pleiades and Orion and say, what is that? Who ordered that? Well, that was Jupiter. And the night that I took that picture, Jupiter and Mars were really close together, so you can exercise for the reader. We can go back and try to look for them later. This is a crazy looking color image of Jupiter. Of course, as I said, James Webb is in the infrared. And so to get it in wave bands that our eyes can see, you need to take the different measurements in the infrared and then push them into the red, green, and blue filters so that they can display on an image. And there you have it with the great red spot looking pretty white. And what's really cool about this is that there are aurora on Jupiter. It has an extremely strong magnetic field. So that's focusing charged particles down onto the poles. And you can see haziness at the north and south pole of Jupiter. Okay, so I said I study exoplanets, and you can go to the next one. One of the most exciting results, if it holds up, from James Webb is something called Jupiter mass binary objects. The short form is jumbos, in the trapezium cluster. So this is in that sword of Orion. If you look down in there, you can find pairs of rather faint things. It's not going to be that easy to see on these images because they're pretty small, but through the James Webb long exposure of trapezium, you can find these pairs. And in those boxes, it shows the pairs and then points out where they are in the image. This is really shocking that these things should be, Jupiter mass bodies should be hanging around each other, because all our best theories have been saying that Jupiter mass planets, or anywhere up to about 6 or 8 Jupiter masses, they shouldn't be able to form out in the cloud. They should all form in disks around stars. And if a Jupiter and we know a lot of Jupiters that are both in such disks currently, even eating mass from the disks. So we do see Jupiters being formed in those environments around newborn stars. But if a Jupiter formed there, how is it going to get ripped off from the star and pull another Jupiter along with it? So the separation between these two planets in these pairs is somewhere between 10 AU and 100 or 300 AU. AU is the distance between the Earth and the Sun. So that's kind of like the scale at which the Jupiter would be orbiting the star, maybe 10 AU. And then it gets kicked out and finds itself bound with another Jupiter at 300 AU. It doesn't make any sense. So this has been a really fun project that's been going on, is trying to understand that. So that's one of my current projects, is to model the theory of how these things can pair up. I mean, current progress, well, I think they probably form as a pair in the cloud after all. All right, next one, please. All right, this is just a fantastic spiral galaxy with James Webb eyes. You can see all the beautiful details. And the next one. This is a rather old picture coming from the ground, but what's special about it is it's a very wide angle. The moon is a half a degree in diameter on the sky, and it's really the best thing. If you have an amateur telescope and looking at it at about this phase or a little bit closer to quarter phase, meaning half of a moon, showing is just the most fun thing, because you can see all the craters. You can pretend you were Galileo, who saw the craters in the first place and told the world about them. And yeah, the moon's the most fun thing to look at with an amateur telescope, so I highly recommend it. What you can also see with a telescope, but not nearly as well, is the very core of this galaxy called Andromeda, or M31. It's the closest galaxy to the Milky Way that's as big or bigger than the Milky Way. We also have a couple of satellite galaxies, And you can see one, in fact, in here. To the top right, there's M33. It's a companion galaxy to M31, small, little guy. So this is a composite because the moon is so bright and the Andromeda is so faint that they're at very different exposure levels. This is just showing you the relative size that they are on the sky. So this is by my colleague at the NSF, Nigel Sharp, quite a few years ago. He was working with a research experience for undergraduates program where they took these images from our national telescopes. So I recall in a graduate school, a teacher talking about Andromeda and saying that it's just so beautiful. It's like gorgeous spiral galaxy, and you know, the ancients, pagans, would worship the sun and the moon and the stars, and if they could only integrate a little longer on their eyes and see the glory that is M31, it would definitely be among their objects of worship. And I mean, that kind of stuck with me. You know, I kind of was using for the title of the talk Psalm 19, which starts, "The heavens declare the glory of God, and the skies above proclaim his handiwork. Day to day pours out speech, and night to night reveals knowledge. There is no speech, there are no words whose voice is not heard. Their voice goes out through all the earth, and their words to the end of the world." So there's something that's can defy, that can speak to all cultures, to all languages, but it needs some technology to get there, which is really quite an interesting fact, that there's something that's deeply poignant about these images, but they were hidden for centuries, for millennia from humans. So it's kind of like God had a little treasure that he had created and put out in the sky to be appreciated, but only at the right time. So let's go on to the next one. So some of those treasures that we can appreciate now require a lot of reflection and mathematical analysis to dig down to really understand what you're seeing. And this is one of the most recent all-sky images of the microwave background. I've been talking about infrared, but this is further out in the spectrum. And this is some evidence for God from a literally cosmic source. And it's called the cosmic microwave background because it's all over the sky. It's completely uniform. There's radiation coming from every direction at a uniform temperature of 2.7 Kelvin, but there's little tiny deviations on top of it, and that's actually what's being shown here. So this is the leftover light from the Big Bang, and each of these little fluctuations is a seed for what will become one of those giant clusters of galaxies that you saw gravitational lensing in the earlier image. So this is 1,000 times, when the universe was 1,000 times smaller, and therefore the gas was 1,000 times higher temperature, and the electrons were still not attached to individual atoms. They were free and scattering light readily. And so that last time that light got scattered, it got scattered toward us, and we're seeing that light here. So what's really fantastic is that God had in mind these galaxies that we saw from the very beginning, providing for the universe enough roughness in order so that they could gravitationally collapse into those clusters. And let's go on to the next one. So this is the schematic of the history of the universe, starting with, you can see that the green and blue map of the early fluctuations there on the left side. These are thought to be, if inflation is right, which is still at the barely tested theory stage. It's about 40 years old, but it's extremely hard to test. So it's an idea that at the very beginning of the Big Bang, there was an exponential expansion that could have blown up quantum fluctuations into these ripples, which then went on to form galaxies in the mature universe. So yeah, without all the pieces just right, either the universe would collapse back on itself, or galaxies wouldn't form and everything would fly off as a continued uniform state. So what's called the growth of structure, the collapse of individual pockets of the universe into galaxies, is something that we can marvel over now as taking both an infinitely wise and infinitely powerful creator to pull that off. All right, let's go to the next one. So that was the cosmic, and here's some evidence of at the microscopic scales that that God had us in mind when he was creating the world. So we're carbon-based life forms, and the story of making carbon is quite remarkable. This is called the triple alpha process. Alpha is just the particle, which is the nucleus of a helium atom. 2 protons and 2 neutrons. So you see 2 of them on the left side and 1 on the bottom. And they have a reaction which makes a very fleeting particle. And this is, you need beryllium, that atom that is very unstable. So when this first interaction happens between 2 carbons, it better be just timed right so that another carbon's going to hit it immediately, so that in the fleeting time that beryllium is stable, a third carbon or a third alpha particle can come in and make the carbon, which is 6 protons and 6 neutrons. Not only this, the usual state for carbon is not at the right energy level to efficiently make this process go. So there's an excited state of carbon, just like electron clouds can have an excited state. Nuclei can also have an excited state, and the carbon atom has an excited state which is at just the right energy level to make this reaction go fast enough. So as these 3 alpha particles come close together, they can skip into the excited state of carbon and then rattle down and form a carbon atom. So the site of this reaction is in the core of stars that are finishing their burning. So it's helium burning, taking helium and making carbon. And this is a process that, if it weren't for the microphysical properties that I just talked about, the excited state of carbon in particular, this site wouldn't work. You need a lot higher temperature, and then all the carbon that's formed in that process would very quickly become other things. So to have any site in the universe that abundantly makes carbon, the microphysics had to be right too. So we had God tinkering on the largest scales, God tinkering on the smallest scales with the laws of physics to accomplish his purposes, which is to make the very good step, what is man? All right, next one. And finally, we're going to alight on my field, which is exoplanets. So this is a plot I made back in 2008, like right after I got my PhD. And this is the current state of the field at the time. I chose a PhD in this field because it was philosophically interesting and religiously interesting. But even for non-religious people, there's a lot of interest in the fact that we had just found a bunch of planets around stars other than the sun. And the thing that really got my engine fired was this observation. This is the plot of all the planets, their orbital periods on the horizontal axis, and it's a logarithmic scale. So our 4 gas giant planets, Jupiter through Neptune, are on the bottom right, those X's. And the vertical axis is how eccentric the orbit is. And so I show a little picture of how to map the numerical eccentricity into the shape of the orbit. So if you get up to 0.99, it's really cigar-shaped. And the planet dives in really close to the star and then flies out again. Whereas our planets in our solar system are all quite circular. Mercury is at 0.2, but the others are pretty close to circles. And so you see the 4 gas giants of ours down at the bottom right, but that's not really the pattern for most of the other gas giant planets, which are the bulk of these planets were Jupiter mass or Saturn mass back at that time. What you can see is a lot of them had a lot shorter orbital periods, even down to 3 days, and that's in fact where that first planet was found in 95 that won the Nobel Prize. 51 Pegasi was a star that has a planet at a 3-day orbit, or 4 days, 3.5, I think. And then a bunch of other planets are found at very, very close in, just like that. So that's like 100 times closer to their star than Jupiter is to our star. So I wanted to work on that aspect, how those planets got down so close to their star, but also this aspect of the orbital eccentricity, because our seasons on the Earth are driven by the obliquity, the tilt of the Earth, but around other stars, it could well be that the planet is eccentric enough that it comes in close to the star, that's summer, and it goes far away from the star, and that's winter. And you can't go too high, or else it wouldn't be habitable anymore. The swings in temperature would be too extreme for animals. So I saw this plot and said, it looks like a lot of other planets are extremely eccentric, especially at that period of about 300 days where the Earth is. These are gas giants now, but if there's so much violence that happens to make these large eccentricities, which is the best theory for how that planets form on circular orbits, but then they kick each other around and become eccentric. Well, that spells doom for most other planets out there in the cosmos. So again, that got my fires going, because I thought, well, I guess God had made a very special place for us, and that we can inhabit, and it's finely tuned. Just as I was describing the fine tuning on the universal scale, it seemed like there was fine tuning at the exoplanet scale. So I promised in the abstract, if you read it for the talk, that there'd be some surprises that it seemingly ruled out now. And this idea that the eccentricities of 0.5 or even 0.9 of gas giants can be applied to otherwise Earth-like planets, in other words, rocky, small planets that are only a 300th the mass of Jupiter. That was my idea, but that seems to be ruled out. So it looks like, let's go on to the next one, and I'll describe how we came to that conclusion. In 2009, the Kepler NASA mission was flown. It's a 1-meter telescope, and it found some 4,000 planets around other stars. And its technique was to stare at the star and wait for planets to go in front of it. So it was just measuring the brightness of the star as a function of time. And when planets go in front of that, it blocks out a little bit. And in a lot of those stars, multiple planets are orbiting around it. And so this is a gallery of all the planets in multiple planet systems. Up to 8 planets are around some of these stars. And then in the bottom left, you see some of the very long period planets. They're just shown as little smiles, because we only saw those planets in 4 years of taking data. Those planets only passed in front of the star once. All right, so we have a lot of planets. I just showed them as circular orbits there, just for ease. We don't really know that from that set of data. But then I did an analysis. This was back in 2012 and 2014, which is the next. Is there one more? Here we go. So this analysis is a little bit wonky, but what it shows is the measurement was how long it takes the planet to go in front of the star. And if you imagine a bunch of planets in the same plane, that are on circular orbits, and they're all going right across the middle of the star, then they should take a certain amount of time to go across the star, because the further the planet is away from the star, the slower it progresses around the star. And so you can calculate how fast the planet should go in front of the star, and then if there's a deviation from that, well, either the system is not edge-on, or the planets are not coplanar with each other. That last statement is the inclination. This vertical axis is the inclination of the planets relative to each other. So instead of lying in a plane, they might lie in a few degrees off from the plane. And then the other thing that can change the speed at which they go in front of the star is the orbital eccentricity. So that's on the horizontal axis here. And it's scaled with respect to the inclination in radians. But the upshot is there was no eccentricity detected. These contours show that you can exclude very large eccentricities, and it's consistent with pretty small eccentricities. And the inclination is consistent with just a few degrees. So if you click to the next one, you'll see where the solar system lies. There's only 8 planets, so there's a lot of uncertainty in this if you do a random sample of those 8. But if you compare the inclination of planets with respect to one another, they fall in this range, about 2 to 3 degrees. So, all right, so the solar system lies very close into a plane, and that's in fact why I saw Jupiter and Mars in the sky near each other, that they pass each other frequently. But and we're in the same plane watching them pass each other. But they also have rather low eccentricities, and so it looks like our solar system is not finely tuned in that respect. Other planetary systems out there share this property that the planets lie nearly in a plane and also on relatively circular orbits. And I can quantify that. It's more circular than about 0.1, so it's very comparable to the solar system planets. So then the philosophical, is that a point against God? Well, not really. I mean, he can make whatever orbit shapes he wants, right? So it's just a point against trying to claim fine-tuning for everything. We still don't know about aliens. We don't have any indication that there are, replicable signals from aliens and or even microbes on nearby stars. So that's going to be the question of the next, several decades at least. If these planets if we can find any sort of evidence of life, even microbial life, on those planets. And that's really one of the main drivers of this field, is to find those planets for which, with James Webb or successor telescopes, like there's one in planning which will be ready in maybe 20 years, optimistically, called the Habitable World Observatory. And this is where the field is driving. Can we find evidence for life on those planets that we're discovering now? You might have seen just in the news this week that one of the closest stars to us, called Barnard Star, was several small planets have been discovered, even smaller than the Earth, around it. That's by the wobble technique, which found the first planet in '95, where the star wobbles a little bit, and spectra of the star tells us if it's red shifting or blue shifting in such a way that a planet is orbiting it. And yeah, a family of little planets was discovered around Barnard Star. So that's the closest star to us besides the sun is Proxima Centauri, and it's in the triple star system. There's Alpha Centauri A and B as well. So they're a triplet, and then this other star, Barnard Star, is the closest singleton star besides the sun to us, and it has a family of planets too. So the upshot is that the universe is pretty full of planetary systems, and so far we don't have dynamical evidence that they're unfit for life, and some of them are being found at the right distance for liquid water to exist on the surface, which we think has the right properties for life to exist. I mean, water is a really special molecule, and so it's not just for convenience that we want to look for it. All right, so if you go on to the next one, I think we'll wrap up by saying I started with a bunch of pretty pictures for you all, and I think that gives us subjective evidence of God's grandeur, power, even eternality from the aesthetic appreciation that we have. That this one might argue that our aesthetic sense, our sense of beauty, comes from evolutionary forces. That it helped us somehow, gave us some advantage in the past. But since this appreciation extends to the physical heavens, and for things that we could never see until a decade or two ago, there's just no evolutionary mechanism that could have shaped it. So whenever you see something beautiful in space and you think, oh, a pagan would have worshipped that, you can say, okay, well, I have some evidence that there's embedded in me an aesthetic sense, a sense of beauty that is calling out to me from God himself. Secondly, the scientific study of creation reveals some intricate details that are just right for the existence and sustenance of life. So the formation of the galaxies in the first place, set up at the Big Bang, the cooking up of elements and stars, which I don't think I mentioned, the formation of planets and disks around those stars, and the existence of carbon on the surfaces of those planets that comes down from to the microscopic properties of atoms as they're forming in the bellies of stars. So yeah, it all cries out for an explanation, and I think we've got one. So there are non-theistic attempts at describing these things. There's anthropic reasoning, which is just saying, well, we're here, so the properties of life must exist to make us here. Otherwise, we couldn't ask that question. Or you could posit a multiverse, that there's properties everywhere, and we just happen to have the right one here. To me, these are both non-answers to these observations that I've been making tonight. And I have not, you've noticed, I've stayed on Job and Psalms tonight. So nature and scripture have often been called God's two books. I've stayed with the poetic and the grandeur verses. I have not gotten into specific theology, but I just want to close here by validating the scriptures teach us how to become right with God and achieve redemption through Christ's sacrifice and atonement for us. And so I'm just a lowly astronomer to bring to you one of those books, but just want to, from the pulpit here, preach a little bit about the other book. So happy to take your questions, and thanks for coming, everyone. Did that pick up? Well, I can phrase it. So you said, did you put any Christian talk in that PhD of yours? I did in the acknowledgments. I quoted that Job one. Oh, they didn't mention it. It's not that they went over their heads. I think it was just they were polite.
We would like to record the questions, so if anyone has a question, I'll bring the microphone over to you. Thank you very much.
Very nice presentation. Just to clarify, you said that eccentricity found in other planets that's similar to Earth's eccentricity, right?
Yeah.
And the same, like they also rotate in the same plane. But the only difference is that in the first plot, you showed that 4 planets from our solar system is quite unique.
Yeah.
But then you showed that they're quite similar. So that's what I don't understand.
Right, good question. So this new set of planets that I was showing from the Kepler spacecraft, they are tending to be way closer into the star. So you also saw in that scatter plot, the ones that are around 3 days, they were quite circular. So it's possible, if you get close enough into the plot, yeah, here. So below about 10 days, you can see almost all of them are below 0.3. So that's one effect, that a lot of those planets that got close in could also be circularized by, we think it's by tidal stretching of the planets, so that there's a giant tidal wave that's formed on the planet by being so close to the star, and that dissipates, and that causes the eccentricity to go down. So that could be one of the mechanisms that gives us this result for the close-in planets that were discovered by transit. People can also measure, so yeah, it remains to be seen whether the rocky planets at 300 days are as circular as the ones that are at 10 days, of order 10 days. So there's still a sliver of a possibility that there's eccentric, that most of the ones near the habitable zone are eccentric. There's another reason for disbelieving that, though, because what we found from the Kepler spacecraft is that these kinds of planets, these more massive planets like Jupiter and Saturn, they tend to be pretty rare. Actually, that was known from radial velocities. So they exist around only about 10% of stars, whereas the rocky planets, they exist around 30 or even 50% of stars. So most rocky planets out there in the universe did not have to contend with one of these really massive eccentric bodies in their system that would have, messed their orbits all up. The most they would have had to contend with is other rocky planets about their own size. And then you can bring in some theoretical knowledge, which is when people do simulations of rocky planets forming, they tend to stay rather circular. The solar system, in fact, is a little bit more circular than most of those simulations would say, but they're not that eccentric. They're like 0.1, 0.2.
Actually, then the question is, can there be different type of life on those extreme planets? Like
Yeah, good
Earth
question.
has quite extreme life forms as well.
Yeah, great follow-up. Earth does have extreme life. That forms the topic of astrobiology, is go look out for extremophiles and hot places. Yeah, so of course the formation and actual habitability of life has got to be very complex. So far as astronomers, all we're doing right now is kind of trying to map out what the conditions would be on the distribution of planets. One of my recent papers was collaborating with the geophysicists at U Chicago to study models of eccentric planets and how their seasonal cycles would operate, even at very high eccentricity. So, yeah, I guess there's other things to worry about just than the temperature being uncomfortable. The main thing to worry about is that you'd lose the ocean entirely. So Venus may have had an Earth-like ocean early in its history, and it simply boiled off into the upper atmosphere, got zapped by high-energy radiation that stripped the hydrogens off the water, and they flew off to space. So this is very likely the reason why Venus doesn't have any ocean right now, is that it's a little bit too close, too hot. And on those high eccentricities, this could happen, but just during it would be a runaway triggered by the close part of the orbit when it's really hot. So, yeah, it's a very multidisciplinary field, going from this astrobiology thing, going from how critters can operate at hot temperatures on up to how planets knock each other around.
Thank you for the fun talk. I had a naive question. I'm not an astrophysicist. You mentioned Jupiter masses plural. I just know of like the singular Jupiter, the planet. So can you just tell us lay people what you mean by plural Jupiter masses?
Yeah, sorry, that was, this means the unit. I'm using Jupiter as a certain number of grams, and then saying it's about 2 times 10 to the 33 grams. So instead of saying 6 times 10 to the 33 grams, I'll say 3 Jupiter masses.
Okay, gotcha. So there's things that are multiple Jupiters worth of mass that are
Yeah.
closely pairing together in surprising ways. Was that the point of that?
Yeah, the
slide?
jumbos, the
Okay.
Jupiter mass binary objects
Okay.
are very surprising that they're pairing together, because we thought that they should form around stars individually, but they don't have a star nearby and they're off on their own.
Okay, thanks. Can I do one more question? The talk about fine-tuning, you mentioned like the rate of expansion of the Big Bang is one example.
Right.
Another favorite of mine is if the ratio of the electromagnetic force to the strong or weak nuclear forces were just off by like 1 in a trillion, as far as we presently can understand, atoms would either explode or collapse, things like that.
Yeah.
I was wondering from your specialty, when I watch debates about this between a Christian and an atheist,
Right.
half the atheists agree the fine-tuning is real and just use the multiverse to get out of the problem.
Yeah.
But the other half say we don't know enough yet, and maybe the fine-tuning isn't really that big of a thing, or even a thing at all. Do you have any thought on like how much confidence empirically or theoretically do we currently have on fine-tuning? I'm constantly surprised by the spectrum of answers I hear from secular astrophysicists or scientists as to how concrete that is or not concrete that is, depending who you ask. So obviously their emotional attitude toward this stuff matters, but do you have a thought, like how much do you think we know on a purely scientific level on this fine-tuning thing being legit?
Right. I think it's not a purely scientific question. I wouldn't call it an emotional one. I would call it a philosophic one. And scientists, sadly, nowadays, scientists don't care about philosophy. So I think the camp who says, oh, we'll just discover someday that it wasn't, there's no tuning because there was no knob in the first place and it's fixed to a certain value because of some logical consistency, they're presuming a lot on the future, in my opinion, to stake a claim that we expect it all to work out well. It's kind of rose-colored glasses that my side will prevail once we know enough. Yeah, so on the other hand, to say, to quit is a bad precedent too. There's the idea of the God of the gaps. If you have a gap in your knowledge, you shouldn't shove God into it because it might get filled with a perfectly reasonable, naturalistic, scientific materialism explanation, and then your God sort of has to retreat from that position. And so I understand the philosophical problem with jumping to that conclusion as well. But it's a conclusion I'm more comfortable jumping to.
So you said you thought briefly hit on, you thought that the anthropic reasoning and the multiverse are non-answers. Can you
Right.
elaborate a little bit more on why you see them that way?
Okay. Well, the anthropic reasoning is, I suppose you can divide it into the thing which is a non-answer, the weak anthropic principle, which is to say that we wouldn't be here to ask the question, I articulated this already, we wouldn't be here to ask the question if not for this property existing. Therefore, since we're here, we don't even need to ask why that property exists, because we know it had to be the case. So I think that's really just sidestepping the question. Strong anthropic principle, on the other hand, is saying there's something special about quantum mechanics that requires observers for existence to, or particles to do what they do, and that's a pretty a big step. But going along with it, it's saying that there needs to be a conscience for the universe to come into existence, and that would be a pretty hard thing to test. So it seems to lie outside of science in the classic demarcations of science about being falsifiable and all. So, I mean, it's a better answer, maybe, but it's still not leaves some to be desired. The other side was, I said fine-tuning and multiverse. So multiverse has some proponents for it based on other physical principles, like the landscape of, I don't know, 10 to the 500 kinds of string theory. So there is some motivation outside of this, but I think the main motivation for it is just that you have these properties that you want to explain, and it's easier to do if you have lots of rolls of the dice. But yeah, you still have to supply your own dice. I mean, like that there should be a structure that even exists that can roll those dice is something that would need to be explained. So I recognize that not all theistic believers in the Big Bang would also say that that God just fine-tuned everything. They might appeal to the multiverse as well. So there are definitely Christian apologists for the multiverse. Yeah, so I just don't see I think already appealing to God to do fine-tuning is enough, that you don't need to. It's a superfluous extra concept to also introduce the multiverse at that point. So, hope I did your question justice.
I have a question about microwave radiation.
Yeah.
Like you showed this. I'm just wondering why those relict radiation still present. I mean, is it because the center of the Big Bang is far, far away from us? Or well, in this case, our like Earth, or our solar system, or galaxy, also run with a high speed, but why this radiation kind of left behind?
Okay, good question. So that conceptual model of the Big Bang is not how I'm reading what how you're proposing the question. Isn't the current conceptual model of the Big Bang. Instead of being at a single place and then you're looking at it, it's more like it's all everywhere at once, and the entirety of the universe is expanding altogether. So there was radiation from where we are now in the universe that was released, and now that's 13 billion light years down in that direction, and in that direction, and in that direction. So we're just happening to look out and see that radiation coming from other places in the universe. And no matter if the Earth were at some place else in the universe, we would see almost the same, the same statistical properties, at least, in the bumps and wiggles of the Big Bang, of the cosmic microwave background. So, yeah.
Okay, thank you. And a technical question. So you showed these nice images of a lot of stars.
Yeah.
And I'm wondering if astrophysicists make three-dimensional images. Like I know, like in microscopy, for example, when you look at a cell or cell nucleus, you still take image from one side, but you then can make a three-dimensional model and rotate it. But I'm wondering if the distances may be too great to make this possible.
Well, in microscopy, are you taking different depths of focus?
Right. Let's say nucleus is like 2 micron, for example, and you see different spots along this axis.
Right.
And microscope can then convert this, and the computer can convert this image into three-dimensional model and rotate it, so you can see sides as well.
Okay, nice.
So, but in
So
this case,
we don't do that. We don't defocus the telescope to see the closer stars in focus and then refocus and see the farther stars. Of course, that doesn't work. But you can wait for 6 months and get to the other side of the solar system, take an image from over there, and so then you have a 2 AU baseline looking at the stars. So the closer by ones apparently wiggle on the sky relative to the farther ones. So this phenomenon is called parallax, and it's been used to great effect recently by a European mission called Gaia to determine the distances to about, let's see if I get the number right. It's a whole lot of stars. I think it's 1 billion stars that they found the distances to. Of course, with varying precisions, but basically the whole nearby Milky Way, this like quarter of the Milky Way, has been mapped out in 3D now by that method. So yeah, we could make a map, we can make a model and fly through it.
So on the, sorry, hearing my voice is weird.
Yeah.
So on the plot where you were talking about the variance in, or variations in transit time and the possible causes, you mentioned that there were 3 possible causes, and one of them was like, 2 of them had to do with the orientation of the system,
Right.
and one had to do with the eccentricity of the planet. How do you determine the differences between those versions? Because I thought that the inclination
Yeah.
of the system to Earth was inherently unknown.
Right. Well, first, it is somewhat known from the length of time the planet goes across the star relative to its entire orbit. Because if it's just skimming the edge of the star, then it would take a very short amount of time to cross it. So you can determine that somewhat in the data. But yeah, astute question. The main thing is that to realize is that plot was very statistical. It was just like, in general, what are the eccentricities and inclinations of this set of planets? And it wasn't trying to nail down the eccentricity. It wasn't that blob that I showed. That was a constraint on the properties of the whole ensemble of systems, and not. It wasn't like a scatter plot of the systems themselves. Okay, so so that means there could be some real funny outliers that had very misaligned orbits, very eccentric, and they would have been missed by the statistical analysis. And all right, so then that being said, there is a difference between total system inclination to the line of sight and mutual inclination among the planets. And the main difference is that total inclination, if they're all coplanar, the outermost planet will always move off the star first as it gets more and more face on. So that means the outer planet will always have a shorter duration relative to what it should than the inner planets. And so that was, in that paper, the first statistical test I did was check whether there was even a signal of that. And there was a booming signal of that. So it said that planets are, on the whole, pretty coplanar. And then that follow-up plot was saying, all right, given that they're pretty coplanar, how coplanar are they? And the answer was 1.5 to 2 degrees. Yeah.
Very good. One more question.
Hello, sir.
Nice talk. So this is a science question, I guess. So the solar system has a lot of rich features like the asteroid belt, the Kuiper belt, and the Oort cloud of comets. I guess this is the 2-part thing. Do you think, how common are those kinds of features for exosolar systems? And 2, how close are we to observationally seeing those types of features?
I'll start with number 2. Of course, we can't see the individual objects. They're too small to see. But when there's collisions among such small objects, they make dust clouds. And these are called debris disks. In some cases, they can be around older stars. And so they're probably not the primordial dust that formed with the star, but rather asteroid belts that are grinding away, hitting one another and throwing up a bunch of dust. And so, yeah, so we do see like 100 million year, 200 million year old stars with dust clouds like that. So that probably indicates they have Kuiper belts or asteroid belts. Not necessarily Oort clouds. So Oort clouds, in our case, they tend to be icy bodies that could make comets if they come close enough to the star. Those are all very small, like a kilometer in size, and they're spread throughout such a large volume of space that they don't hit each other and grind down and make something visible. So I would say that the only purchase we have on how many comet clouds there are, or clouds there are around other stars, is how many comets we're going to start to see flying through our solar system in a few years, because we found two, Oumuamua and Borisov, this is a few years ago, comets that are not bound to the sun but are flying through on hyperbolic orbits. They happened to come by pretty close to the Earth so that we could see them. But yeah, we will have a new telescope. This is a national telescope called Rubin, taking night after night images, and we'll be able to see more interstellar comets like that. So once we get, in about 5 or 10 years, we'll have a catalog of 10 or maybe even 100 interstellar comets, and then we can start to say how many other stars must have comet clouds as well. That's the plan. All right.
Great. Well, thank
Thank
you
you
very
all.
much, Doc. Could you all express appreciation for Dr. Fabrici? Thank you. Great. Just a couple of things to mention. Our next event that you might be interested in will be at the Bradley Study Center on October 22nd. We have the director of another Christian study center who's coming into town and doing a live, it'll be an in-person podcast recording with Dr. Lee Vinsel, who's a professor here at Virginia Tech. And the topic is the question of technology and the question of the human. And Mike Sakassis, our primary speaker, is well-known Substacker in technology and culture. So we're looking forward to that. And Lee Vinsel is a professor in the Science, Technology, and Society program here at Virginia Tech. And they're good friends, and I think we're going to have a really great evening. And that's October 22nd. The second thing you might want to know about is that we are helping to bring onto campus December 3rd a production of the Screwtape Letters that'll be in the Moss Art Center on December 3rd. Tickets are going to sell out. I can just tell you right now, they're going to sell out. And we've probably sold most of the student tickets already through Campus Ministries. If you're faculty, staff, you can get a discount through the Moss Art Center. It's not on the Moss Art Center's regular promotional calendar, but if you go on there and to buy tickets, you'll see it on their regular calendar, and you can buy tickets right now directly from the Moss Art Center December 3rd, and we're really looking forward to that. We brought this production company came in 2 years ago and did a fantastic event, and we sold out the Moss Art Center, and we fully expect to do it again, and that'll be December 3rd. You can see it on our website. You can see it on the Moss Art Center website. So thank you very much for coming tonight. I hope you enjoyed the conversation, and I can tell you the students that participated today and are coming back tomorrow morning, we have really appreciated the leadership of Dr. Fabrici. So thank you. Have a good night.